Very good evening, everyone. So, as you all know, that today we will going to study about the electrochemistry chapter. Further, like today is the part 3 for the theory of electrochemistry, and hope you are very well and doing very well, right? So let's start. Okay. Yeah. One thing that if you have any doubt in between the lecture, while I am explaining, you can ask in the chat box. Okay. Now let's start. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Now, please note that the parts of the content may have been generated using the generative AI, which is experimental. Okay, so what is the objective of today's lecture, which you are attending right here? So, after attending this lecture, you will be able to derive the Nernst equation and to derive the relation between the standard potential of cell and the Gibbs energy of the cell reaction and their equilibrium constant. Okay, so this is the objective. And what are the topics that we will going to cover according to the NCRT? So the Nernst equation, first of all, which is marked as 2.3 as our section, 2.3 in our NCRT textbook. And the second topic is marked as 2.3.1 in our NCRT textbook, and the topic is equilibrium constant from the Nernst equation. Then next subsection we will going to cover is 2.3.2, which is electrochemical cell and the Gibbs energy of reaction. And example includes 2.1 to 2.3, that means 2.1, 2.2, 2.3, which will comes under this topic, and some in-text question 2.4 to 2.6. That means 3 in-text question and 3 example we will going to cover. Okay, so our first topic is 2.3 Nernst equation. Nernst equation, okay, so Nernst equation is the main topic of today's lecture, and it is an equation, as the name says, equation. It is an equation through which we can calculate the EMF of a given cell using the standard value of EMF. Okay, in the previous lecture, as you know, we have covered some detail or some information about the EMF of the cell, about the potential, about the galvanic cell, about their working, and about the electrode potential of half cell. How can you determine that, right? So here the Nernst equation is saying that it is an equation through which we can calculate the EMF of a given cell using the standard value of EMF. Okay, now standard value of EMF means which are already defined. Previously, we have studied the electrochemical series, right? The series where our reaction is given in the reduced in which we have the reduced form of iron, we have the oxidized form of iron, they are reacting, and their reduction potential or their E0 value is also given, right? So that E0 is the standard value of EMF given. So with the use of that E0 values, E0 of EMF, or you can say EMF, we can how can we calculate the EMF of a full cell, okay, of a given cell? That for that the equation we will use is known as the Nernst equation. Now, as we know that the concentration of all the species involved in the electrode reaction is unity, right? This need not be always true. Okay, So until now we have studied that the concentration of all species, as we have discussed about SHE, right, standard electrode, hydrogen electrode. So until now we have seen that the concentration of all species involved in the electrode reaction is unity. That means we have been taken the concentration of the species as one. Now here we are saying that this need not to be always true in all the cases. Now Nernst showed that for the electrode reaction, which is this, suppose we have an electrode following this reaction, Mn positive plus n electron giving us the M metal, right? So we can say that this is the reaction which is associated with the electrode reaction, right? So EMF is basically electromotive force. Okay, the electrode potential at any concentration measured with respect to standard hydrogen electrode can be represented by, so the electrode potential at any concentration, okay, at any concentration means here we are not considering the concentration as 1. So if you want to tell the electrode potential for any concentration measured with respect to the standard hydrogen electrode, as I said, SHE, that can be represented by E, given E for M from N positive going to M, is equals to E naught. This is the standard potential for this electrode reaction, minus RT by NF ln M upon Mn positive. Okay, now if you see this equation we just written here, right here, so E naught here is representing the standard electrode potential for this electrode reaction of metal M, which is, reducing because it is gaining the electrons, becoming the metal in the solid state. And this E we are writing here is the EMF or the electrode potential of the whole cell, cell which we are using here. And the half cell we are taking as standard hydrogen electrode other than this electrode reaction. Okay, so standard hydrogen electrode and this electrode which is having this Mn positive plus an electron giving us M reaction. So this makes a complete cell, and for that cell EMF determination we are writing this equation as E of this electrode is equals to E naught of this electrode minus RT by NF ln, you can write it as concentration of the product divided by the concentration of the reactant. Product as the M metal which we are gaining in the neutral form, and initially the reactant is in the N positive, so the reactant concentration, that is Mn positive. Okay, RT by NF you can consider it as constant, only N is variable depending upon the reaction, because N is this, the number of electrons which are gaining or losing by some metal in the reaction. Okay, that is N representing, F is our Faraday, and R is our gas constant, T is our temperature. Mostly this E naught value is, known to us sometimes, and then E we can calculate. Okay, so continuing to the Nernst equation, but the concentration of solid M is taken as unity, and we have E of Mn positive to M is equals to E naught of Mn positive by M minus RT by NF ln M. Now M concentration we have taken solid M. Okay, solid M which we are gaining or which we are obtaining through the electrode reaction. That solid M concentration we are taking as unity, that is 1. So we place the 1 in the numerator of the ln and divided by Mn positive concentration. Okay, this is the equation, NCERT equation 2.8, which is marked, or you can easily find out in our NCERT textbook in the electrochemistry chapter. Now, as the E naught of Mn positive to M has already been defined, R is a gas constant which is 8.314 joule Kelvin inverse mole inverse. N is the number of electrons which is involved in the redox reaction, which our species is either gaining or releasing. F is a Faraday constant whose value is 96487 coulomb mole inverse. E of Mn positive to M is electrode potential of Mn positive going to M cell, and E naught of Mn positive to M is standard electrode potential of Mn positive going to M. T is the temperature in the Kelvin units, and Mn positive is a concentration of species Mn positive. Okay, which the reaction you have just seen in the previous slide, that is the Mn positive concentration we are using here in this equation for determining the E of Mn positive going to M. Nernst equation for Daniell cell. Then how can we write for a Daniell cell the Nernst equation? Okay, first of all, here we have a question that can any non-metal be used as electrode ever? So mostly we use the metals as our electrode because in the cell structure the metal electrode is used because there is a gaining or losing of electrons. There is a this electron taking place and giving is going on in our cell. That is why we generally used the metal. But as you know, the graphite is the allotrope of carbon, and it can be used as we use the electrode as a we use the electrode of graphite in many of our cells. Okay, as we can use the graphite electrode, and graphite is also a good conductor of electricity, so it is generally used in dry cells and electrolytic cells. Okay, just we have covered very before, right? So yeah, we can use the non-metals as the electrodes in some of the cases. Okay, in the Daniell cell, the electrode potential for any given concentration of copper 2 positive and zinc 2 positive ions, we write. So in the Daniell cell, if you want to find out the electrode potential for the given concentration of copper and zinc ions, we write for cathode the reaction will be for the copper, because at the cathode the reduction is happening, right, in the case of copper ion. So the Nernst equation for that will be E of copper 2 positive to copper is equals to E naught of copper 2 positive to copper and minus RT by 2F ln 1 by copper 2 positive aqueous concentration, right? So this E of copper 2 positive to copper we are determining in this equation, and this is the equation in this is NCERT equation marked as 2.9 in our question in our NCERT chapter. Okay, and E naught is the standard reduction standard potential of the copper electrode, and minus RT by 2F. 2 is because the number of electrons which are interchanging or which are participating in the redox reaction is 2, right, as the charge says. So copper from the 0 is going to copper 2 positive, right? Or you can also say copper 2 positive is gaining 2 number of electrons and becoming copper in the 0 state. So 2 number of electrons are involving in the redox reaction in the reduction process of the copper electrode. That means we are taking N is equals to 2 here and ln 1 by copper 2 positive aqueous. Why we are taking 1? Because we take the copper which we are gaining here, the metal which we are gaining here in the neutral state concentration as 1, and the rest ionic concentration of copper 2 positive is taken in the denominator. Okay, so this is the equation for the cathode which is of copper in our Daniell cell. Okay, next is that for anode, of course, if we have covered the cathode. So anode, for the anode we are using zinc, right? So the zinc e of zinc to positive to zinc will be E naught of zinc to positive to zinc minus RT by 2F ln, again 1 upon zinc to positive aqueous. Now at anode we have oxidation, that means the zinc to positive, no, the zinc is releasing our electrons and becoming zinc 2 positive plus 2 electrons. Okay, so zinc is releasing the electrons and going from 0 to the plus 2 state and undergoing the oxidation process at the anode. So for the anode, the Nernst equation will be E of zinc to positive to zinc is equals to E naught of zinc zinc to positive to zinc minus RT by 2F ln 1 upon zinc to positive concentration. Now here again we are using n equals to 2 because as I said that two number of electrons are involving in our redox reaction. So we are taking here the n equals to 2 value. Okay, so okay, in the Daniell cell the standard electrode we used is copper and zinc. Okay, it is already mentioned in the NCRT chapter in the electrochemistry that the standard electrode we use in the Daniell cell is copper and zinc. Otherwise there is no that necessary that you have to use these two only. You can use who can easily participate in the cell reaction without converting from, like, without involving in the solution or without electron transfer. Okay, so which are suitable for the Daniell cell process, for the Daniell cell mechanism, that metal electrode you can use in the Daniell cell. But in the NCRT we have given, as we are going according to that, we have given that in the Daniell cell we use the standard copper and the zinc electrode as the cathode and the anode. Okay, so for the equation 2.10, so this is the NCRT equation 2.10 marked in our electrochemistry chapter in the NCRT textbook. Okay, this is the anode Nernst equation. We are talking about the Daniell cell where we are having copper and the zinc electrode, and at the cathode we are undergoing the reduction process. At the anode we are undergoing the oxidation process. We have already covered that what is oxidation, what is reduction. Oxidation is releasing of electrons, reduction is gaining of electrons. So when the copper 2 positive is gaining 2 number of electrons, it is converting to the copper 0 state, copper neutral state. And when zinc is releasing 2 electrons, it is undergoing the oxidation process. Okay, so at the anode the oxidation is going on, at cathode the copper reduction is going on. Now if you write the Nernst equation for the cathode, it will be E of EMF, or you can say EMF of the cell or EMF of the electrode potential, electrode copper will be equals to E naught. This E naught, as naught is coming, this is the standard potential of electrode copper minus RT by 2F ln 1 upon copper 2 positive aqueous. So here we are writing 1 because we are considering the concentration of this copper we are gaining after the reduction process is 1. Okay, that's why 1. And this is also the equation number 2.9 marked in our NCRT chapter electrochemistry. And the anode, as I said, that at the anode oxidation is happening, that means zinc is releasing 2 number of electrons. So if you want to write out the EMF for the anode, the Nernst equation will be E of the zinc electrode is equals to E naught, that is standard potential of zinc electrode, minus RT by 2F ln 1 upon zinc 2 positive in the aqueous medium. Okay, 1, again we are considering here the metal in the neutral form, concentration as unity, and 2F because the N here, N is initially we are taking N value and N is here 2, that's why we are writing 2. N is basically the number of electrons which are involved in our redox reaction. Okay, if you see in these two reactions of oxidation and reduction and oxidation, the N is 2. Why? Because 2 number of electrons are gaining or losing by our elements which is undergoing the oxidation or reduction process. Okay, that's why the N we are taking here 2 in both the cases. And these are the equations 2.9 and 2.10 marked in our electrochemistry chapter in the NCERT textbook. Okay. Now continue on this. The cell potential. Now the cell potential, E of cell will be E of copper 2 positive to copper electrode minus E of zinc 2 positive to zinc electrode. Okay. Okay, one question is again that what is 2F? As I said, 2F. Okay, 2F. F is a Faraday constant. As it is a constant, it has some value 9644847 something, and 2 is basically N. N is the number of electron which is participating in our redox reaction, as zinc is releasing 2 number of electron and copper is accepting 2 number of electron. That means N equals to 2. The number of electrons which is involving in a redox reaction is 2. There is 2 electrons which are joining or losing by our elements. That is why we are taking N value as 2, and that is why we have written the 2F in the denominator as per the Nernst equation. Okay, Nernst equation is E equals to E naught minus N minus RT by NF ln the metal concentration divided by the ion concentration of the metal. Okay, here N is representing the number of electrons which are participating in the redox reaction. Okay, and in the redox reaction, the total number of electrons which the oxidized and the reduced element are gaining or losing, that is 2. Okay, 2 number of electrons. That is why we are writing RT by 2F. Okay, so the Nernst equation for the cell potential. Okay, so 96500 is basically the. Okay, so as it is a constant, we have different values of Faradays, but they are approximate to this value. They are nearby this value. Okay, if we are taking 96487 something, that will also be the nearest to this value. Okay, we just take the approximate value of the Faraday constant, and I am suggesting that whatever the value of F is given in our NCERT textbook, kindly consider that. Okay. Okay, now let's continue. So if you want to find out the cell potential will be equals to E of the cathode minus E of the anode. The cathode is copper cathode, and the anode is of zinc metal, right? So the EMF or the cell potential of the potential of the cell will be E of cathode minus E of anode. Okay, so cell potential is basically the potential difference between the two electrodes present in our cell. Okay, as I am defining here. Okay, so if you know the structure of the cell, there are two beakers in which some electrolyte, you can say solution is present, and the solution, let's suppose it is having zinc sulfate solution. So zinc electrode will be dipped in this solution, and if it is having the copper sulfate solution, then copper electrode is dipped in this, and they are connecting by a wire through which externally the current is flowing and the electron is traveling or electron is moving from anode to the cathode. Let's suppose this is anode, this is cathode, electrode. Okay, this electrode is anode, this electrode is cathode. Okay, now they have their specific electrode potential. Okay, electrode potential. They have their specific electrode potential, but as the cell is constituting both the electrodes together, which are joining with the wire, so cell potential is basically the difference between the two electrodes. So we are defining it as the electrode potential of cathode minus the electrode potential of anode. That is cell potential. Okay, so here it is also written that in the Daniell cell we are using the copper as our cathode. So this electrode is made up of copper, and this electrode we are using as anode is made up of zinc. So E of, or you can say electrode potential of copper, electrode potential of cathode minus electrode potential of anode. Anode is made up of zinc. Now E of cell will be, now we just put the value of E of copper and E of zinc as we have derived in the previous slide according to the Nernst equation. Okay, so E of copper to positive to copper will be this much. E naught of standard potential of copper to positive to copper minus RT by 2F ln 1 upon copper ion concentration. Okay, and minus, this minus will come here minus, and this E of zinc to positive to zinc will be this. E naught of zinc to positive to zinc. Here initially in the Nernst equation we have minus, but as minus is already present here, so we just multiply this minus inside the inside this equation for the electrode potential. So minus of E naught zinc positive to zinc, and minus minus will become plus, plus of RT by 2F ln 1 upon zinc ion concentration. Okay, so this is the overall cell potential. Now we simplify it. How? So as you know, this is the E naught value and this is the E naught value. That is the standard potential value of the electrodes. We take these two together. So E naught of copper to positive to copper minus E naught of zinc to positive to zinc. They both are coming together. Now the remaining values are this one, and this one. Minus of RT by 2F ln 1 upon copper 2 plus concentration, and plus of RT by 2F ln 1 upon zinc 2 plus concentration. Right, the remaining are these. Now if you see, RT by 2F term is common in both the terms, right? RT by 2F coming here also and here also. So what we have done, we just take the RT by 2F common, here bracket will come, and we take the minus RT by 2F as common. Okay, minus sign is also important. We take minus RT by 2F as common, and whatever the remaining term will be, that will be put in the bracket, in a closed bracket. So if you take from this term, the minus RT by 2F common, the left will be ln 1 upon copper 2 plus concentration, right? Similarly, we write this here, ln 1 upon copper 2 plus concentration. And here we have taken RT by 2F and minus sign at the outside. Okay, but it is positive. This is positive, right? So we have to put one negative so that when you open this bracket, it will become same. Like this term will become negative, and this term after the minus minus multiplication will become positive. Okay, so here the remaining will be minus of ln 1 upon zinc 2 plus concentration. Now this is the simplification. Now we will more specify it or simplify it. So thus the E of cell, the cell potential, will be equals to the standard cell potential minus standard cell potential is this. Okay, which is E naught of copper 2 plus to copper minus E naught of zinc 2 plus to zinc, or you can say E naught of cathode minus E naught of anode. Okay, so we take this E naught of cathode minus E naught of anode as E naught of overall cell. Minus will come because here it is minus will come and it is in bracket. So minus of RT by 2F ln this minus ln this will be ln this term. Okay, this we have derived by using the logarithmic conversion. So basically we have ln this by this minus ln by this by this. That will become ln this term upon this term. We used here the logarithmic conversion. If we have ln A minus ln B, okay, you can write it as ln A by B. Simply we have done here. We have write 1 upon copper 2 positive upon 1 upon zinc 2 positive. This will go here and this will go in the numerator. Okay. So this will become zinc 2 positive upon copper 2 positive, right? So as this is written here. So the cell potential finally will become equal to the standard potential of cell minus RT by 2F ln zinc 2 positive upon copper 2 positive. Okay. This is ln. This is ln. Okay. Ln means logarithmic thing we are using. It has different table, different values like log 1, log 2, ln1, ln2. You can study it in detail in your mathematics subject. Okay. And okay, here reason is also given that as E naught is equals to E naught of right hand side electrode minus E naught of left hand side electrode, basically cathode minus anode, which I described here for this E naught of cell value, right? So this is the equation, NCRT equation marked as 2.11 in our NCRT textbook. Okay. Now let's study about the significance of Nernst equation for the Daniell cell. The cell potential depends on the concentration of both copper 2 plus and zinc 2 plus ions. Okay, so as they are the metals by which our electrode are made up of in the Daniell cell, right? So whatever the concentration of zinc 2 positive and the copper 2 positive ions are, the potential of the cell will depend on this, upon their concentration. Okay, because we are taking, if you have seen the Nernst equation, we are taking the zinc 2 positive and copper 2 positive ions concentration in the logarithmic term, right? So the cell potential is depending upon the concentration of the ions. It is increases with increase in the concentration of copper 2 plus ions. It increases with the decrease in the concentration of zinc 2 positive ion. Okay, so if the copper 2 positive ion increases, the E of cell potential will increase. And if the concentration of zinc 2 positive ion decreases, the cell potential will increase. So this is the case. You can derive it or you can relate it from the Nernst equation. As we know that E of cell, that is cell potential, is equals to E naught of cell minus RT by 2F ln zinc 2 positive upon copper 2 positive, as we have discussed this equation, which is marked as 2.11, and on the basis of this we have write these 3 points, which are the significance for the Nernst equation for the Daniell cell. Yeah, so basically in the Daniell cell we have two ions only, because we have two electrodes only made up of two different metals. So they will only produce two different type of ions. Now convert the natural logarithm in equation 2.11. Okay, we have just seen equation 2.11 where, okay, let me write it again. E of cell equals to E naught of cell minus RT by 2F ln zinc 2 plus upon copper 2 plus. This was the equation 2.11, right? So we convert the natural logarithm this to the base 10 and substituting the values of R, F and T we will take as 298 Kelvin. So we can reduce this equation 2.112. E equals to E naught of cell minus 0.0591 by 2 log of zinc 2 plus upon copper 2 plus. Okay. So this is again we have used the natural logarithm conversion to the base 10 log conversion. So what we have done, we have ln zinc 2 plus to copper 2 plus, right? And before this we have RT by 2F. So we have taken the gas constant value. We have put it the gas constant value, the F value and the T value as 298 Kelvin, and here 2 is already present. Okay, so if you know this and 2 is already present, you can solve this fraction, right? So let's suppose this fraction is x. Okay, now you can convert this Ln zinc 2 plus 2 zinc 2 plus upon copper 2 plus to log base 10 zinc 2 plus to copper 2 plus. How? By multiplying it by 2.303. Okay, so you have to just write it like x is this fraction value, multiply by 2.303 log zinc 2 plus upon copper 2 plus. Okay, so this is nothing but this equation, that 0.0591 by 2 is coming at this place, x times 2.303. Okay, so the cell potential can also be written as E naught of cell, standard potential of cell, minus 0.0591 by 2 log of zinc 2 plus upon copper 2 plus. Okay, this is the NCERT equation marked as 2.12 in our NCERT textbook. We should use the same number of electrons, that is n, for both the electrodes and thus for the following cell. This is the cell of nickel and the silver. Nickel to nickel 2 plus, salt bridge, Ag plus to Ag. Now, if you want to write the cell reaction, it will be nickel plus 2 Ag positive, giving us Ni2 plus, nickel 2 plus 2 silver in the solid form. If you see that nickel is here in the neutral form going to 2 positive, and silver is in the positive form going to neutral form, right? So it is a redox cell reaction for this particular cell representation. Now the Nernst equation for this cell reaction can be written as E of cell, that is cell potential, equals to the standard potential of cell minus RT by NF. Now N again is here 2. We are taking N equals to 2. Why? Because 2 number of electrons are participating in this redox reaction. Okay, so nickel is going from 0 to plus 2. That means it is gaining 2 electrons. And 2 silver ions becoming 2 Ag. That means 2 silver in the solid form in the neutral state. That means both the silver ions are gaining 1 electron each. That means total 2 electrons. Right? So the number of electrons, the N value is same in both the cases, reduction and oxidation. So that's why we are taking N equals to 2 in the Nernst equation of this given cell. Okay, so this is the Nernst equation for this given cell, where we have written the cell potential equals to the standard potential of the cell minus RT by 2F ln nickel 2 plus upon Ag plus whole square. Because why the square? Because the coefficient of the silver in the reaction is 2. Right? So nickel 2 plus is in the aqueous form. In the product side, so we write here nickel 2 plus, no coefficient is present, so we don't write anything in the power, it will be 1. And the Ag plus has 2 because in the reactant side the Ag plus or silver plus is in the aqueous form, and the coefficient here before the silver is written as 2, so we are writing the Ag2 plus concentration square here. Okay, so this is the Nernst equation for the cell reaction. Now, how can you write the Nernst equation for a general reaction? For a general electrochemical reaction of the type AA plus BB after exchanging of n number of electrons becoming CC and DD. This small a, small b, small c and small d are representing the coefficients for the reactants and the products, and this capital A, capital B, capital C and capital D are our reactants and products. Okay. Now Nernst equation for this general reaction is written as, or can be written as, cell potential equals to the standard cell potential minus RT by NF. N is this number of electrons which are participating in this cell reaction, ln Q. Q is representing reaction quotient. And what will be the value of Q? So the cell potential equals to the standard cell potential minus RT by NF ln. So Q will be C, that means the product upon the reactant. Okay, the product upon reactant. So the products are this and this. So C and D and their coefficients to the power. Okay, in the power the coefficient will come. So C coefficient is small c. So here small c. The D coefficient is small d. So small d divided by the reactant. Reactant is A and B with respect of their coefficient as their powers. So A coefficient is small a. So their power in the small a. And the B coefficient is small b. So their power is small b. This is the representation of reaction quotient which we are writing here as Q. Okay, so this is the cell potential for a general reaction by using, okay, this is the cell potential by using the Nernst equation for a general reaction. This is the NCERT equation marked as 2.13 in our NCERT textbook. Okay, let's see one example on the topics or the concepts we have covered. So the example is that represent the cell in which the following reaction takes place. So the reaction is magnesium reacting with two silver positive ions having the concentration 0.0001 molar, giving us magnesium 2 positive having concentration 0.130 molar plus 2 silver atoms, okay, in the solid form. Calculate its cell potential if the standard cell potential is given as 3.17. Okay, so the example is saying that represent the cell in which the following reaction takes place and calculates its E cell. E naught cell is given. So if you will solve this, how can you solve this? So first of all, we have to write the cell. How can you represent the cell whose reaction is already given? So the representation of cell will be like this. Magnesium to magnesium 2 positive. The magnesium 2 positive is having this much concentration. Salt bridge, silver positive to silver. The silver positive is having this much concentration already given in the question. Now we have to identify the E of cell, right? So E of cell, that is cell potential, we write or we use by the Nernst equation. Okay, we have just studied the Nernst equation which gives the E cell value. So E of cell, that is cell potential, equals to the standard cell potential minus RT by 2F ln magnesium 2 plus divided by silver plus whole square. Here again we are using the product upon reactant thing, that in the product we are gaining the magnesium 2 plus ions and in the reactant we have silver positive ions. Okay, so one thing to remember, if you are given a reaction, cell reaction, so something is present in the reactant side and the other things are present in the product side. Okay, if our species are in solid form or the liquid form, you cannot consider that while calculating the E of cell using the Nernst equation. Okay, this ln something by something, you can only written here the terms or the species which are present in either aqueous state or the gaseous state. Okay, that's why we are only using magnesium 2 plus and silver plus. But we have two reactants, so we can write here the two reactants concentration, but we are only writing silver plus concentration because it is an aqueous form in the reaction given. So E of cell using the Nernst equation will be standard potential minus RT by 2F. Here again N we are taking as 2 because two number of electrons are interchanging between the oxidized and the reduced species. ln the product, which is magnesium 2 plus divided by the reactant. Reactant is silver plus having the coefficient 2, so it will come in the power 2. Okay, RT is basically the multiplication of R and T representing temperature and R is representing the gas constant. Simply you just have to put the value, the E naught of cell, that is the standard cell potential is already given in the question. So we just mention here 3.17 volt minus RT by 2F. Okay. In the previous slide, we have seen the Nernst equation where we have solved this fraction, right? And convert the ln to the log term, log base 10 term, right? So we use that thing. So this fraction will become 0.059 divided by 2 volt, and log magnesium 2 plus is 0.130 here, and silver positive is 0.0001 molar, so 0.001 whole square. Okay, now you just have to solve this equation. First you have to solve the log of this, so you have to first divide 130 divided by 0. This you can write as 10 to the power minus 4 whole square, right? 4 times 2 is 8, so 0.130 divided by 10 to the power minus 8. And you can also take this here, it will become plus 8, then power will come at the multiplication term. So after you have to just know something about the log and ln here, their properties, logarithmic properties, ln properties, their values. Okay, what is log 1, what is log 2, what is ln1, ln2. Then you can solve these type of examples or questions related to this chapter. So when you solve this whole term, it will be 0.21 volt. So 3.17 is the standard cell potential. So 3.17 minus 0.21, you have to subtract it, and it will be 2.96 volt. Okay, so the cell or cell potential, E of cell, is coming out as 2.96 volt, and we are deriving it, or we have derived it by using the Nernst equation. Okay. Okay. Now let's continue to our next subsection, which is coming under the 2.3 section. So it is 2.3.1, which is equilibrium constant from the Nernst equation. So to calculate the equilibrium constant using the Nernst equation, if the circuit in the Daniell cell, which is already present in our figure 2.1, is closed, then the reaction takes place. Okay, if the circuit in the Daniell cell is closed, then the reaction is taking place. Circuit should be closed. What does that mean? Let's see the figure 2.1. This is the figure 2.1. Okay, figure 2.1 has two beakers, this one and this one. Okay, so for the example, you can refer to the NCERT textbook. It is mentioned there. Okay, and it was simply that you have to identify, or you have to determine the cell potential of the cell, and by using the Nernst equation. Okay, and in that we have used the logarithmic terms and their functions. So you have to study about the logarithmic properties, and then you can solve by putting the values given, and simply you can get the cell potential. Okay, this was about the example. You can refer to the NCERT textbook. I can't go back. Okay, so if the circuit in the Daniell cell is closed, so what we are saying, that this is the circuit of the Daniell cell in the figure 2.1. We have two beakers, each is having one electrode, zinc and copper, and the salt bridge are connecting the two solutions for maintaining the neutrality of the solution. These two electrodes are connected externally, through which the current is flowing and the electron is flowing, right? So we are saying that circuit in the Daniell cell is closed, then the reactions takes place. Daniell cell having electrodes of zinc and copper dipping in the solution of their respective salt. It has a solution of zinc sulfate, it has a solution of copper sulfate. So as the time passes, the concentration of zinc 2 positive keeps on increasing, while the concentration of copper 2 positive keeps on decreasing according to the following reaction. So we have already seen the diagram for the Daniell cell. So we are saying that if the circuit is closed, as the time passes, the zinc positive concentration keeps on increasing, and the copper 2 positive concentration keeps on decreasing, and they are according to the following reaction given. The reaction is zinc plus copper 2 plus converting to zinc 2 plus to copper. Okay, so zinc is oxidizing because it is going from neutral to 2 plus, and copper is reducing. It is going from 2 plus to 0 state. Right? This is the reaction or the equation of NCRT marked as 2.1. At the same time, the voltage of the cell as read on the voltmeter keeps on decreasing. We have connected a voltmeter. If we connected the voltmeter in the circuit, the voltage at the same time of the cell as read on the voltmeter keeps decreasing. After some time, what will happen? There is no change in the concentration of these two ions, and at the same time the voltmeter gives 0 reading. Okay, so we are studying here right now that how you can calculate the equilibrium constant using the Nernst equation. So I am defining a process that in the Daniell cell, if the circuit is closed, as the time passes, the concentration of zinc 2 plus ion will increase and copper 2 plus ion will decrease as per this given reaction which is happening in our Daniell cell. And at the same time, the voltage in the voltmeter keeps on decreasing. But after some time, what will happen? That copper 2 plus and zinc 2 plus change in concentration will stop. There will be no change. And at the same time, the voltmeter gives 0 reading. That means 0 volt will be the reading you can see in the voltmeter. This indicates that equilibrium has been attained. Okay, so at this condition where the voltmeter gives 0 reading, that means there is no concentration change of the two ions of electrode is taking place in the reaction or in the cell. That means we have attained the equilibrium. Now in this situation, the Nernst equation may be written as, now in this situation, that means equilibrium situation. How can you write the Nernst equation at that time? It can be written as the E of cell equals to 0. The EMF is 0 because the voltmeter is giving 0 volt reading, right? So the cell potential becomes 0, and 0 is equals to E naught of cell minus, we convert the ln to the log by multiplying by 2.303 and remaining are same, RT by NF. N is 2 because 2 electrons are gained or lose by our species, and log zinc 2 plus upon copper 2 plus. This is the Nernst equation, right, in the case of equilibrium. Or you can take this E naught of cell at one side and this negative term at another side to make it positive. So E naught of cell can be written as E naught of cell equals to 2.303 RT by 2F log zinc 2 plus upon copper 2 plus. Okay. And R is gas constant, as I said, T is temperature, F is Faraday constant, and 2 is the number of electrons which are participating in the redox reaction. Now at the equilibrium, the zinc 2 plus upon the copper 2 plus, this term is equals to Kc for the reaction. That means equilibrium constant for the reaction, which is 2.1 reaction. We have seen the 2.1 reaction in which the zinc and copper are reacting together, copper 2 plus ion, right? So that equation is 2.1. So zinc 2 plus upon copper 2 plus, that means the product concentration divided by the reactant concentration is equals to the equilibrium constant of reaction 2.1. So at the 298 Kelvin temperature, the above equation can be written as the equation we just have seen. E naught of cell, standard potential of cell equals to 0.0591. So we solve the 2.303 RT by 2F. Okay, so this 2 is written here the same, and 2.303 R value we know because it is a constant. T value we put at 298 Kelvin, and F value is a constant, so you can determine the F value and you can put it here, solve this fraction. So it will be 0.0591 by 2 log, and this term is Kc, equilibrium constant for the reaction. So log of Kc. Okay, and when you solve it or at the stand or at the equilibrium, it is considered to be equal to 1.1 volt. Okay, because the standard potential of the cell at the equilibrium is 1.1 volt. So log of Kc will be, we just rearrange this. We know that at equilibrium E naught of cell is taken as 1.1 volt, E of cell is taken as 0. Now if you know that this term can also be equal to 1.1 volt, right? So we just rearrange this term. Okay. So let's see. We have a Daniel cell reaction we just studied, in which the zinc and the copper 2 plus ion are reacting with each other, becoming zinc 2 plus and copper, right? So zinc is going from neutral to 2 plus, it is oxidizing, and copper 2 plus is going from 2 plus to neutral, it is reducing, right? Now as you know that the Nernst equation, this is the equation reaction 2.1. Now as you know, Nernst equation is that E equals to E naught minus RT by NF ln the product is zinc 2 plus, so zinc 2 plus upon reactant is copper 2 plus. They both are only present in the aqueous form, that's why we are taking here the product upon reactant, zinc 2 plus upon copper 2 plus. It can also be written as E naught minus 2.303 RT by 2F, in this case because 2 electrons are involving in the reaction, zinc 2 plus upon copper 2 plus, right? Now at the equilibrium, we said that when the equilibrium is attained in the Daniell cell, the E of cell will become 0. Okay, so 0 is equals to E naught minus, now you can solve this term, right? How? You have 2.303 multiplied by R is a gas constant which has a value. T we are taking here 298 Kelvin. So 2.303 multiplied by R value multiplied by 298 divided by the Faraday constant value, which some of you just have said that 96500 you can take. So when you can solve this fraction, it will become 0.0591 volt divided by 2 is same here. Okay, and here will come log zinc 2 plus upon copper 2 plus, right? Now what we are saying that as zinc 2 plus upon copper 2 plus is product concentration upon reactant concentration, which is the definition of equilibrium constant for any reaction, which is represented by Kc. Kc is equilibrium constant of a reaction, and it is defined as the concentration of product upon concentration of reactant. Okay, in this case, in this reaction 2.1, the product is zinc 2 plus and the reactant is copper 2 plus. So zinc 2 plus upon copper 2 plus will become equals to Kc, the equilibrium constant. Okay, so we write this equation 0.0591 upon 2 log of Kc equals to 1.1 volt. Okay, now how this 1.1 volt come? This is also the thing that the value of E naught of cell we have taken at the equilibrium time, at the equilibrium position is 1.1 volt. So this E naught cell equals to this whole term, and E naught of cell is also equals to 1.1 volt, right? That means this term will also be equals to 1.1 volt because E naught of cell is 1.1 volt. Okay, this region is also given. So now we just rearrange this thing. So log of Kc, so we just take the variable thing at one side and the number thing at the another side. Okay, so 1.1 volt, this 2 will go in the multiplication, 1.1 multiplied by 2 divided by this 0.059 volt, and when you solve this number, this fraction, this will become 37.288. Okay, so this is the log Kc value we have just derived to 37.288. Okay, so the value of RT is always given. Yeah, it is mentioned always. If you solve a question where you are using this Nernst equation, there will be a given of R and the T values and the F values. Okay, so in the Nernst equation we have just putted the given values and derived and solved that equation, and then we get this term, okay, which is given. And then we know that E naught of cell is 1.1 at equilibrium, so we put it equal to 1.1 volt, and then we solve for the log Kc because it is only the variable, and log Kc is coming out as 37.288. And from this you can derive the Kc by taking here log base 10 is present. Okay, so if log base 10 is given, here it is given Kc. Okay, if log base 10 Kc equals to 37.288, you can write it Kc equals to 10 to the power 37.288. Okay, this is the logarithmic conversion. So as I said, you have to consider the study of log here in this chapter for understanding of the questions and the examples. Okay, so Kc will be equals to 2 times 10 to the power 37. You just solve this at the 298 Kelvin. T equals to 298 we have to take. Okay, so Kc value is coming out as this much at 298 Kelvin. What we are studying, that how to calculate the equilibrium constant using the Nernst equation. So using the Nernst equation, this is how you can calculate the equilibrium constant for a reaction. Okay, I will suggest that study about the log, how the log can you convert, or how, what is the values of logs, what is it stable, and what are the properties of logs. You can consider the mathematics portion or mathematics subject, because there it is given about the log, which you can also consider as a syllabus of JE. Okay, JE covers the logs. Okay, thank you so much for joining this session, and soon your next faculty will join you for the physics. Okay, thank you so much.